Well, thank you for joining this session. My name is Patricio Cofre. There you have my Twitter handle. I'm from EY Metric Arts. I'm partner for data and AI back in Chile, Santiago de Chile. And I'm also Microsoft AI MVP and regional director. And today I'm going to talk to you about how to leverage AI and the edge in public transportation. And I'm going to tell you a story on how we use these two novel technologies in a real case in the city of Valparaiso in Chile. Okay, so there it is. So the agenda for this 15 minutes or so, first of all, I'm going to talk about the public transportation in Valparaiso, tell you a little bit more on the number of stations, the number of cameras that are in place in there. Then the challenge and goal we identified in order to face this problem. To show you a little bit of the architecture that we implemented on how we use the platform to solve this scenario. And finally, some results and next steps that we have achieved and we want to keep go ahead. So Valparaiso is the main port in Chile. It's probably the first big city of the country where everything started, where everything started to move in the country. The city moves around 10 million tons a year, and it accounts for around 30% of the total exportations of the trade of the country. Its transportation system runs for 43 kilometers. It has 20 stations and transports some 25 million passenger trips a year. So it's not a huge transportation system, but it's enough for the city that is the second largest in the country. Fare evasion is a huge problem in my country. Actually, and it's also a pretty complex problem because it's not only people not paying the fare, but also the whole social impact and the whole social motivation for them to do that. It's not only a matter of money, it's also a matter of justice, and they created some ideas that they have the right to evade and to avoid paying the fare. The number of evasion in Chile is around 35%. It means 1 out of 3 is not paying the fare. So it's really a huge and complex problem. Any current schema on trying to tackle this problem present a high linearity between the number of the covered area with cameras and the number of people behind this camera trying to catch some behaviors. So in this linearity is where AI takes place. If now we need to jump to 40 stations or we need to jump to 400 cameras, probably we'll need to jump to a 10-fold number of people having a look of the cameras. And this is one of the main problems. In the same image that you're looking in here, probably each one of these analysts take care of some 20 cameras. So what's the real probability of catching a behavior in there? And this is part of the problem, and this is where the AI came in. This project looked to add AI, allowing to classify behaviors such as the fare evasion or the benefits misuse. That is other phase of the evasion, when you use a benefit that do not belong to you. And this is part of the two problems that we faced. So two main questions might arise when I say this. First of all, why AI? Why we need AI? And second, why we need the edge? Why not to put everything on the cloud? So some problems are pretty difficult to solve using traditional algorithms and procedural programming. I mean, Can you write a code that says if something and if other and while something, this can be classified as evasion? It's kind of difficult. So these all are called the ineffable problems. The problems that probably we as humans, and even a child, can detect pretty easy, but it's very difficult to put in code, in traditional procedural code. So for example, to identify objects and people in photos and videos, probably your kids can do it, and can identify mom, can identify dad, can identify grandpa. But how to put that in code is really challenging. To recommend a product based on historic data, something that the retail used to do, and some expert in the retail do it pretty well, but to put it in code is pretty challenging. The same for detecting failures in industrial processes, or one of the biggest AI projects in place, that is the autonomous vehicle. And it's probably one of the projects that is moving the whole AI movement forward, and most of the advances in AIs are being produced by trying to solve this problem, the autonomous car. So I'm going to focus on the first one, on trying to identify objects and people in photos and video. And as a rule of thumb, for images and videos, if a kid of 4 years old can do it, probably you can write an AI that can do it. And this is kind of the similarity that we are reaching up to this point. Okay? So if you say, is in this photo mom? Probably a 4-year kid can say, yes, he is. Or is it grandpa? Is it an elder? And probably a 4-year kid can do it. And this is how we need to start thinking. Not in programming, but in showing examples, tagged examples, and eventually this AI will learn and we can use it. So just to revisit the machine learning process, first of all is to prepare data, to try to gather video streams in this case, from the whole set of cameras of the metro station, and prepare the data. Tag cases of evasion, put video in the right format, identify some features. Then we move to build and train. And one of the nice things of the platform is that it allows you to write the training mechanism in the framework that best fits to you. So in our case, we use extensively the TensorFlow, but if other teams prefer to use Caffe, Keras, or PyTorch, it doesn't matter. It will create for us objects, pre-packed objects that we can push to an edge device. So, and this is interesting because the evaluation, even though you do the whole training in the cloud, the evaluation do not need to go to the cloud. So new cases evaluation, what is called the inference, just need to happen in place, just need to happen in the same place where video is being captured. And this is called the edge. And for the next slides, I'm just going to talk about the edge. I'm just going to talk on inference in the same metro stations where things are happening. And what's the advantage of this? And why AI on the edge? First of all, because we need very low latency. We need to solve the case where things are happening. We need to raise alerts in the exact moment that an evasion is happening. Second, if the whole thing will be created on cloud, probably will going to be expensive. If I need to keep my GPUs machines turned on the whole day for the whole for a year, for a couple of years, probably will be very expensive. So the idea is to create the models in the best place, that probably is the cloud, because of the elasticity and capacity to scale, but then create an object and put it in place in order to have cheap and almost free evaluation and inference in place. So this is why the scalability matters, and in our case was critical, otherwise would have been impossible. And finally, the flexibility, because sometimes you do not have, and especially in Latin America, in all places, in all the station, good access to the internet, good access to good network, and eventually not even good access to continuous power supply. So this kind of solutions in the edge allows you to have a device with batteries, making inference by themselves, and so on. So I hope I have answered the question on why the edge, and this is pretty important. So in high level, the architecture that we implemented, everything starts from the devices, capturing streams of video and pushing it into a local edge device. And in the local edge device, we are doing a couple of AI tasks. So first of all, we are identifying human figures. From the human figure, we are detecting heads. And from the heads, we are detecting and cropping faces. And are just these faces what we are sending to the cloud through this path. So in the normal flow path, we are sending just faces, 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 faces. They are all being ingested for big data analysis, passed through the cognitive services, and that's how we are detecting the age, the gender, and try to see if it matches with the car with the card that the guy is presenting in the turnstile, and then it moves all the way forward to the reporting and in a lot of reports that we done for the transportation system in Power BI, and I'm going to show you some examples in the next slides. But there's other path that you see here below. That is the alert flow task. So when we see someone showing a card, and we see in the camera, so we have one structured data set, that is the turnstile, and we have other unstructured data set, that is the video, and I see that somehow these do not match. For example, I do not have a turnstile card passing on, but I do have video, probably it's evasion. If I have a card of a student and I see someone of 50s or 60s, probably is an evasion as well, and in the opposite way also. So in that case, we do not pass through the whole infrastructure steps. We pass straight to a web app where an analyst can see in a tablet all the cases and try to do some decisions on how to face the specific case. To do the processing, to do the inference, we have many options. First of all, and the most flexible options are always the CPUs. In CPUs, you can write in almost any language. It's pretty mature on what you can code and what you can put in the CPUs, but are still slow, and probably you need a lot of CPUs in order to solve this problem. Then we can jump to the GPUs. With that, so far we have a nice feature, nice runtimes that can run in the GPUs. However, they are a little bit more expensive. And now, probably the next steps will be to think on the FPGAs, and Microsoft is doing an excellent job with the Azure Stack Edge that is comprised of FPGAs. New versions will have GPUs as well, so we can choose the one that best match. And moving to the right, we also have the ASICs that are extremely powerful compute options, but are completely hardwired, so are less flexible, but very, very, very efficient. So you can do inference in a very, very low latency. So here are more or less some of the results. You see, in this heat map, what you see are faces, are the number of faces passing through the camera. This is being done at very low latency, all being processed in the edge. So it's been processed by one of these devices. Actually, is done by this one. It's called the NVIDIA Savior module, yeah, which is a pretty powerful GPU compute. It's a relatively small box like this. And if we see that there's a face passing by and I don't see a turnstile record, I will raise an alert and it will be put it into a web app like this so the analyst can take action. The other case is the benefit misuse. So I see a card, a benefit card that is of this guy, that probably is a former military or have a third age benefit, and I see a person that do not match. And how we do that? We have two options. First of all is to make face matching. That is a feature that the cognitive service have. Or we can just take the features. Man, a certain range of age, and in this case, also take the gender, take the range of age, and if I see a mismatch, I can raise the alert for the analyst to have a look at it. So all of these cases are falling into a platform like this one, where I can list all the cases. We use some color scale to see cases that probably have some mismatch, and the analyst can take action first by facing the person, or just to blocking the card. So user will need to face the officials trying to recover his card because it's useless at this point. So one of the good things is that for the first time, we are offering to the transportation system of Chile a map of the problem, a map of the evasion. So other than the immediate alerts, if we can put in a dashboard, things like this, where the problem is happening, when the problem is happening, what is the stations where it is happening, where the problem starts, probably they can do best public policies and try to really tackle this problem. As I said at the beginning, this is not an easy problem. It's not only a technological problem. So probably by looking at the dashboard, they can take better decisions and they can eventually try to go to the root of the problem, understanding where it starts, how it starts, and how it flows. So we're pretty much on time. Here you have my Twitter handle. Contact me whatever you need. I'll stay here in the side if you have any questions. Okay, so thank you so much.